The chi-square test for association solves our problem of multiple tests by creating one test for the whole table. Now our null and our alternative hypotheses are always pretty much the same, except that they will be written in terms of the variables that are relevant to your particular problem. Our null hypothesis is no association, and our alternative hypothesis is that there is some association between the two variables. So we have two categorical variables here, and those are degree held and astrology, or views about astrology. So the chi-square test for association is appropriate in situations where we have two categorical variables. If we contrast this to the chi-square goodness of fit test, that was for one categorical variable, where we were comparing it to some preconceived idea of what it should be equal to in all of its, or what the counts should be equal to in all of those categories. So this is for comparing two categorical variables to see if there's any association. Again, we have the idea of expected counts. We have a slightly different formula for expected count. This is row total times column total divided by table total. So if we fill in the row and column totals that we already calculated, 237, 120, 357 for the table total, and we had column totals of 75, 184, and 98. Then each of these calculations is going to look like, if we're in junior college, not scientific, we want the row total of 237 times the column total of 75 divided by the table total of 357, which comes out to be 49.8. If we do the same for the other boxes, following the same formula, we see we're always dividing by 357 because the table total really doesn't change from one cell to the next. We end up with these expected counts calculated. The formula for expected count for the goodness of fit test in one variable is a little bit more intuitive than this one, and the way to understand this formula is to think about it in two separate pieces. Suppose that what we were doing was first calculating row total divided by table total. What that would get you is the proportion of everyone in the table who is in that row, right? So it's the proportion of the table in that row. When you then take that value and multiply it by the column total, you're saying, I'm going to redistribute my column the same way I've redistributed, or the same way I've distributed the whole table. So the table total of 357 has 237 in row 1, 120 in row 2, which is a proportion of 0.663, I then take that number and I multiply it by my column total to get how many I have in row 1 of that column, right? So this might allow it to be a little bit more intuitive why the formula is what it is, but knowing the formula certainly is sufficient for being able to fill in the table. And the idea of the expected counts is really still the same as what it is for one variable. It is how we think these numbers from our table row and column totals should be distributed if there is in fact no association between the two variables. So our chi-square test statistic is also calculated the same way. Here I have it laid out in the same order as the table, so that while I'm calculating this first contribution, I am looking at the row 1, column 1 of my table. So that's going to be an observed count of 44 minus my expected count of 49.8 divided by my expected count of 49.8. Now I suggest that you fill in the 2 remaining and see if you get the same thing that I do. Go ahead and pause the video for just a moment. And you should get these values. Whoops. At first I accidentally filled in the same thing twice. You should get these values here corresponding to the observed and expected counts in those corresponding cells. We get a total chi-square test statistic in this case of 3.6. So this is still called my chi-square test statistic, and we're still going to look at it in a chi-square distribution. Until we know our degrees of freedom, we're really not in a very good position to judge whether this is a large value or not. It looks small enough that it's unlikely that this is going to be considered very large. But let's go on to finding out what our degrees of freedom are so that we can complete the test. So for our chi-square distribution, recall that in one variable we said it was the number of categories minus 1. Well, here we have categories for both variables. So for one of the variables, that's going to be the number of rows minus 1. For the other variable, that's going to be the number of columns minus 1. And what we do is we take the product, we multiply. So in our example, we have 2 rows times 3 columns, and therefore we have 1 times 2, or 2 degrees of freedom. So here is a graph of a chi-square distribution with 2 degrees of freedom. Our chi-square statistic is 3.6, which places it just a tiny bit to the right of 3.5. And this is what our p-value will look like. It's this area of this tail here, to the right of 3.6. Now, when we're trying to estimate p-value, I recommend we always start with 10%. Is this more or less than 10%? I would definitely say this is more than 10%. So going up, is it more than 20%, right? I would say it's hard to say. It's somewhere between 10 and 20%, probably somewhere between 15 and 20%. So maybe I would come up with 17% and call it 0.17. It's okay as long as I get any number that's more than 10% and that's clearly less than 50%, right? Even if you thought this was about a third, I don't think it's anywhere near a third of the area. But if you came up with a third and said 0.3 or 0.33, that would be okay too. We're really going for the process and a ballpark figure. Now we can go into StatKey and see what StatKey says it is based on a chi-square distribution with 2 degrees of freedom. So from StatKey, theoretical distributions chi-squared, this is where we're going. Asks for degrees of freedom first, I enter 2, and I get this graph, right tail, overwrite this value with our 3.6, and StatKey comes up with 0.165 as my p-value. So this estimate of 0.17 was very close, really closer than we should expect to be in general. In both cases, we would fail to reject at any reasonable level, because we would fail to reject even at the 0.1 level. And so we would say that we do not have statistically significant evidence of an association between astrology and degree held. So we do not have statistically significant evidence of an association between degree held and views about astrology. We would generally want a two-part conclusion for this, just like we did with chi-square goodness of fit, but since we didn't get statistically significant evidence, we would not include part two. We're not that interested to see where there is statistically significant evidence if there isn't any at all. But also, let's just take a moment to put this back in context of the problem of multiple tests. Looking at these individually, we thought that maybe we would reject the idea that P1 equals P3, that the proportion of junior college degree holders who think astrology is scientific is equal to the proportion of graduate degree holders who think that astrology is scientific. But when we look at the whole table together, we fail to reject. So looking at this, if we wanted to look more closely at this comparison, what we would have to do at this point is just start over with a new independent data set and just look for this comparison and see if this still seems to show statistically significant difference, right? So we would start over with a new data set if we really still wanted to look at that one comparison in particular. But for a very quick tour of StatKey with this test, we are going to go to chi-square test for association. That's beside more advanced randomization tests. We'll click on edit data and type this in manually. It starts with that blank there because that aligns, the word blank aligns with the labels, not with numbers. And therefore we need an empty space there, just like you can see if you go back to your original table, you'll see an empty space in that first location. And then just comma separate all of the labels and the numbers to get the data entered correctly. So here in StatKey, chi-square test for association, beside more advanced randomization tests, edit data, type this in exactly as shown with commas in the right places. Go ahead and leave data has header row checked because we do have the labels of junior college, bachelor, and graduate up there. And then verify that this table looks the same as the table that you were trying to enter. That gives you your chi-square test statistic of 3.619. And if I click on show details, I can see the whole table with observed counts, expected counts, and contributions to chi-square, just like we saw with the goodness of fit test. And so we looked at show details. Let's now also go to a chi-square distribution with 2DF. And see what the p-value is that we get out of StatKey. Remember that to do this, we have to exit this screen and go back to StatKey, come down to Theoretical Distributions chi-square, enter our degrees of freedom, click on right tail, then type in our 3.619, and we get a p-value of 0.164 from this slightly more accurate chi-square test statistic. So this is how we would get all of the information that we spent a little bit more time doing partially by hand using StatKey instead. With these multiple comparison tests, get in the habit of going to two different screens. You first go to a screen for your test where you get your test statistic and some more detailed information. You then go back to the home screen and go to Theoretical Distributions to go to your actual distribution where you get your p-value. Even though it is possible to get a p-value using the randomization distribution, we are going for theoretical distributions more in these later sections. So get in the habit of going to the correct theoretical distribution after you've gotten your test statistic from the test page.